Okay, so I'm Martina. I met already some of you. And today and tomorrow, Anne back there and I will hopefully guide you through from the very basic of what movement is to some analytical tools that we can use to analyze mainly the geometry of track. So without bringing in environment, only looking at the track as a geometric element. So let's talk about movement data. Cami already said movement is location through time. To define what time is and what locations are, so what coordinates are, we need some definition because we first of all need all to agree on how we find things on Earth. How do we place things on Earth? And so for that we need a reference systems, which can be easy, but we need to take a lot of things into account. So we can start from the shape of the Earth. It's a geoid. And then maybe this is some repetition for some of you, but what we can start with is a geographic coordinate system. This is a spherical coordinates, and it uses angles to find locations on Earth. So we have the equatorial plane, which is defined by the natural rotation of the Earth. But then we have some other axes that are defined by us. We have the prime meridian that divides the eastern from a western hemisphere. We have latitude and longitude that are our coordinates, and latitude goes from minus 90 in the South Pole to plus 90, and longitude from minus 180 to plus 180. So it uses 360 degrees longitude, 180 latitude, and probably you have seen already some of these different ways to define coordinates. So it could be in decimal, degrees, decimal, minutes, or decimal, degrees, minutes, and seconds. But then we also need a projected coordinate system. And this is because our computer screens are flat, maps are flat. And so to represent a point that is on a spherical object on the plane, we need a way to project this, to transform it so that we can find it also in 2D. The problem is that if you try to flatten, for instance, the skin of an orange on a flat surface, you will realize that it's not possible to do it without creating some crinkles on the skin. And these are basically distortions that are natural to all our projections. We can't get away from it. So here you can see, for instance, on the left, we have some circles of the exact same radius at different latitudinal points on the Earth. And then when you project it on this specific projection, you see that the ones at the top have a different area than the ones in the middle. So there will always be some degrees of distortion, and we will learn how to deal with it or how to use the type of projection that fits our purpose, because there are so many available. So there will always be some distortion in the shape, the area, the distance, and so on. And this is just an example of how the different continents look in their shape and size in different projections. So what is a coordinate reference system? We looked at the geographic reference system and the projected system. All of these are coordinate reference systems, and they are made of different parts. So on the left, we have the real shape of the Earth, and then on the right, we have just like some axis and some axis on 2D. And then here in the middle, we have what is called the coordinate reference system, which is mainly made of two parts. We have a datum, and this is basically the geometric the geometry that we decide to use to approximate the shape of the Earth. It's an ellipsoid, but this can have different measurements for their axis, for instance. So the most commonly used is the WGS84, but there is others. And then after we define what is the shape, then we have some sort of algorithm that we as biologists usually were not very interested in, but it just tells us basically how we can fit this much surface on the sphere on this much space, more or less. So you need all this information. And so here to summarize, a CRS is always composed of a datum, a coordinate system, which is this algorithm, and then the unit, which can be degrees or can be meters. And there are also different ways to, for instance, see what is the coordinate reference system of whatever object we are working in. Can be in R, can be in a geographic information system, or anywhere else. And these are just different ways to express the exact same information. And in R, it used to be very common to use this proj4 string, and now it's becoming more useful, more common to use this EPSG. And here there is a couple of links, the one to the left especially, that give a lot of information about even just what type of projection you might want to use. So you can just Google like the country that you're interested in, because there is a lot of projections that are just local for one place, or just how to transform, for instance, from one description to another one, EPSG to Proj4 and so on. So very useful links. So what projections to choose? There is many, and I would say Googling for your region is always the best answer. It depends mainly on the scale and the purpose of your analysis. So if you work a global scale, there are some main suggestions. And you will see also in the package that Anne will present you later, we can easily work in geographic coordinate system, so in spheric coordinates. You don't have so much to worry about the projection. But then if you are interested in a specific area and very local movement, it could be very handy to have coordinates in meters. And then you can look for just a small scale, for instance, UTM, if your area is very small. But it really depends. And here also there are some different links that you can use to even just explore what it means to have some location in what projection, what happens when you transform it to a different projection, and there is some interactive tools to understand this a bit better. So now that we agreed on how we define space, how do we use these coordinates? And the main purpose of using coordinates is to represent the real world in some form that we can analyze or quantify. So there are spatial data models, and we divide them mainly in two main groups. Raster data are basically grids that tell us at each point in the space that we are sampling, how does the vegetation look like, or how does the elevation look like. So it's a continuous description of what we see on the ground. And then there is vector data, that is what we are going to talk about now, that is mainly points, lines, and polygons. So very simple features, simple representation of objects. These two types of spatial data, they also have different packages that we use to work them in R. For the vector data, I'm going to briefly talk about this now with SF, and you also will see a lot of examples in the next days. And then on Thursday, you will hear more about Terra, that is the successor of the raster package and will be used for analyzing more remote sensing data. So vector data, as I was saying, is just points, lines, and polygons, and one make the other. So coordinates here, now you know that they can be in different coordinate systems, but basically it's just two points, two values giving you the position on this coordinate system. The sequence of these positions can make a line. The sequence of lines in different combination can make polygons. And there are also different data formats that are used to work with vector data. It used to be very common to work with shapefiles, but shapefiles were made of many different files, and it was not very convenient. Files could get lost. And now I think the most common is probably geo package. So vector data in R, as I was saying, we use SF. That is, means simple features. And a simple feature is any object. And here you see to the right, any object can be made of other objects. So there is many different types of vector data. So you don't only have line, but you also have multi-point, multi-line, multi-polygon. So the structure is quite complex. But on the left, you can see that mainly any of this SF object is made of a mandatory component, which is the spatial part. So it's called geometry. And this is what in R is actually the class SF. But it's a complex object that has different classes in it. And so on the right, you see that there is another attribute that is optional. You don't have to have it, but you can have it. And it's basically a data frame or a table, which is basically all additional information that are associated to each geometry.
Question.
Yeah.
So you could have...
the microphone.
So you could have a file that is an...
Please.
So you could have a file that is SF without a table, but you cannot have the other way around, right? Or like you cannot transfer information that you have on a table to create SF.
No, you can. You can make an SF object out of a data frame. We will see how in maybe in the next script, I think, as long as there is coordinates in it. So the only mandatory component to make an SF object is having coordinates, which then become the geometry. So this is a data frame until you tell R that it's not really a normal data frame, but it's a data frame with spatial components in it. And so you can just specify always, I think we will see now. You will just specify what columns contain the coordinate information and what is the coordinate reference system. Yes, so this is just, again, a different explanation of the same, but what is very important here is time. So movement, we said that it's locations in time, and we talked now a lot about how we define locations, but then for movement to be defined as movement, we also need a time component. So we will talk in a few minutes about a package that deals with this, and you will have an extension of the SF object that contains coordinates, any non-spatial attribute, but then makes also time mandatory for it to be movement. And of course, we talked about space, but we didn't say anything yet about time. And things are easy, but never as easy as they look. So it's quite straightforward, but there is a few things we always need to take into account when we talk about time. And that's also why Kami was talking about the importance of standardization. So are we talking about the same coordinate reference system? Are we talking about the same time zone? And so always when we need to explore, import movement data, there has to be a few questions that come to our head even before we start looking at the data. And these are what time zone our GPS or device records in. Usually is universal time, but not always, so it's not always UTC. Most of them are. Is the animal tracked crossing time zones? Because if the animal is at the border between time zones and the device is collecting in local time, then you will have these time switches all the time of 1 hour, for instance. The daylight saving switches as well. And then once we enter the data in R, then we have to make sure we declare in which time zone we are working, because then from there downstream, all the rest will be affected by the definition of time and space. So talking about time, it's not that complex. In R, it's quite straightforward, but a few things need to be taken into account. One is, for instance, in which time zone our computer is recording. Because if we don't specify or declare the time, whatever object we define is likely to take whatever time zone our computer is in. And then when we want to transform from one time zone to the other, a very useful function is this also names, because when we transform our GPS UTC time in anything else, this anything else time zone might have a different name in your computer or in your computer or in my computer. In terms of code, it's very straightforward. We work with an object that is called POSIXity, and there is always this 3 component. One is the actual time string that usually is a character string, and this could have very different format. But then in the second argument, we define how is this format. So in which order the month, the day, and the year are given. And then there is this other argument, the TZ, the time zone, that tells us in which time zone this was recorded. And then only after this is set, then we can very easily transform it to any local time zone that we are interested in. So here we see in UTC time, today at 2 will become in Central European summertime, which is what we have right now, 2 hours later. But it's very important that the first one is declared. So this is the distinction between declaring the time zone and converting to a different time zone.
There's a question. Anna, I'm coming.
So I have a question regarding when you have the animal in 2 different time zones.
Mm-hmm.
The data, so it will recognize where the animal was, like depending on where the animal was moving. When you're downloading the data, it will be already in each different time zone. And the other question is when we upload this data on MoveBank, it will also recognize the region that you have the data, or do you need to update, like to change which zone you want to work?
As far as I know, MoveBank does not do it automatically, right? You have to specify in which time zone the data are recorded.
Yeah, MoveBank. So when you upload the data to MoveBank, you have to just specify the time zone of your timestamp variable. So, and that is assumed to be the same for the entire variable. So, and I mean, if you're working with GPS, most manufacturer reports UTC time, but you have to know it. There's no reason why you should believe them, because some do actually also deliver local timestamp. So if you upload UTC to MoveBank, MoveBank will translate it into local time. And from knowing where the positions were, the local time is correct, but it's not going the other way around.
Yeah,
So,
exactly.
yeah. There was a question here? Same, yeah. And again, I mean, just to kind of re-emphasize that, you have to know the coordinate reference system of the data that you have. There's no way you can guess it. You have to know it, and the time zone that the timestamp has been collected in. You have to know that. And typically, if you got it wrong, you will not see your data. If you can't see your data, this is when because like, wait, they said something about coordinate reference system. That's when you got your points in another space.
Yeah. And now we're not talking about environmental data yet, but this is a very common problem when you either have two different data sets that you didn't realize were in two different coordinate systems, and then you try to plot them together and you don't see them, or you want to plot your points on top of whatever environmental layer, and then you don't see your data. That's usually one of the problems. Yes, and just to conclude, I think, before I pass it on to Anne, the Move2 package is what I just mentioned before, and it's a library that offers a series of functions to import, visualize, and also do some analysis on movement data, and it's an extension of SF, so it's a successor of a package that already existed up to 2 years ago, the Move package. And then because of all the libraries that have changed, spatial libraries, maybe some of you are aware, all this change between SP and RGDAL and then SF. So this is kind of following up on these big changes. And on top of that, also a lot of things are more efficient, just faster. And Anne will now talk about this, and also here you find some useful links for Move2.
Are there any questions for Martina? Or remarks? Things that you happened to learn the hard way you want to share with others?
So yeah, I learned the hard way. The time savings. How do you deal with time savings when your animal is I don't know, one part of the season in one time saving zone and then it changes? Do you need to like split your data set and change it, or yeah?
Yeah, it really mainly depends on what you want to do. So if you work in UTC, it doesn't matter. If you work on local time and you have this the daylight saving switches, then if you want to interpret your data, then you will have to transform it only that part of your data to the timestamp in that moment, because otherwise you will have like suddenly a behavior. I don't know if we are looking at the time at which an animal goes into the den, for instance, and for a big part of your data set, you have this happening at 5 p.m. and then suddenly you have it at 4 p.m. or 6 p.m. It's not the animal changing, but this.
Yeah. Okay.
Just to follow up on that, I work a lot with camera trap data, not with movement data until now. With camera trap data, we would convert time to relative to sunrise and sunset. Is that something that happens with movement data as well?
You can do that. So there's packages where you can calculate the angle of the sun at that place at that time, and then from that you can have a more continuous measure of the natural light conditions. But the thing is, still, you will, if you want to calculate kind of local time, you need to, and this is why daylight saving really is a pain. Forget about daylight saving, because there is a reason why 12 o'clock is at when the sun is highest. And so this would be my approach would be to just skip daylight saving, because the real ecological, biological relevant time is winter time in that sense. It's when actually the sun is in its zenith at 12 o'clock. And that's so for any datum between, I don't know, somewhere in March until October, just deduce an hour, minus 1 hour, and you get back the winter time or the real time. Other than that, think about, maybe it's sufficient for you to work in UTC. If you're looking at time differences, then you can completely stay in UTC, because it doesn't have this relevance to the sun, but it's all the timestamps are in the same time zone, so you can calculate time differences. You can also, what you can also do is calculate sunrise, sunset in UTC for that place, and then you calculate it relative to sunrise and sunset in UTC in that time. But important thing really is that we are all aware time is not as easy as it seems. Yeah, especially if you are given data by people who open it in Excel and all these kind of no-goes, because then all sorts of things happen to your data.
Never do that, please.
Yeah, just send Excel back. Not touching this.
Any more questions? Yeah.
Suppose your animal is moving across multiple spatial zones and you're using something like the UTM. Is it possible to like stitch together different zones for those ranges it covers, or not really?
Not
No,
so
you just have
easily.
to choose one that covers
Yeah.
a larger area. Okay.
Yeah, I would say UTM is really good if your animal moves within that zone, which is something between 100 to 800 kilometers, depending on where you are on Earth.
But even if it moves a little, it could like be at the edge of the tile, and then be even if it just moves in 1 square kilometer, if the square kilometer falls between tiles, it's just where it falls. So yeah.
Then again, it depends what you need to do. So if you are calculating distances, that might be a problem. Then you have the
Yeah.
distances calculated at the margin of the range of these animals that are off or very different to the way you calculate the distances for the rest of the track. And anyway, also if you want to do analysis with the environmental layers, it's just easier if you have an environmental layer that has a projection that it's meant for larger scale analysis.